today's goal of this lecture, today I am going to describe about unique factorization domain, which is called as shortcut UFD. At first I will discuss what is the irreducible element, what is the definition of associated. Then today's goal of this lecture. Today I will see what is the unique factorization domain. Irreducible element. Let R be commutative ring with unity 1. A non-zero non-unit element. This is very important. A non-zero non-unit element P belongs to the ring R is said to be irreducible element if for all AB belongs to R, P equal to A times B. Either A is unit or B is unit in the ring R. Then we can tell the element P is irreducible element. In Z, in integer, 3 is a irreducible element. Why 3 is a irreducible element? At first think oneself. 3 written as AB where either A is unit or B is unit. Notice in Z unit are 1 and minus 1. We can write 3 as 3 times 1 where 1 is the unit of Z. Similarly we can write this as minus 1 times minus 3. We can write this as 1 times 3. Also we can write this as minus 3 times minus 1. Notice here 1 is unit. So 1 and minus 1 is the unit in Z. So 3 is irreducible element in Z. Actually in Z, if P is a prime, then P is irreducible. Irreducible element. Actually in Z, prime element and irreducible element always be coincide. But otherwise, this is not true. Consider Z6. Is prime imply irreducible element? No. Let me see it. In Z6, class 3 is a prime element. Why? Let class A and class B belongs to the member of Z6 such that P equal to class 3 divides class A times class B. That implies class 3 divides class AB. Then by definition there exists class C such that class AB equal to class 3C. That imply obviously 6 divide AB minus 3C. And since 6 divide AB minus 3C, that means 3 divide AB minus 3C. And since 3 divide AB minus 3C, that implies 3 divide AB. And since AB belongs to integer, so that implies either 3 divide A or 3 divide B. That means that imply either class 3 divide class A or class 3 divide class B. Therefore, class 3 is a prime element in Z6. But class 3 is not irreducible element in Z6. In Z6. Why? Because in Z6 class 3 equal to class 3 times class 3. But class 3 is not unit in Z6. So class 3 is a prime element, but this does not imply irreducible element. Prime and irreducible element, they are different. Only Z, they are both coincide. Is alpha equal to 5 is irreducible element in Zi? No. Element in Zi? No. Because we all of us know in Zi units are look like 1 minus 1, I minus I. And 5 equal to in Zi 2 plus I times 2 minus I. Here neither 2 plus I nor 2 minus I is unit of Zi. So 5 is not irreducible element in Zi. Actually, the prime ideal and prime element both are different. The definition of prime ideal: P belongs to integer is prime if P divide AB, then that imply either P divide A or P divide B. But this division only true for Z, otherwise this is not possible. For any ring division not possible. So P belongs to Z is a prime element if and only if ideal generated by P is a prime ideal of the ring R. And this is valid for all ring, because if ideal generated by P is a prime ideal, then the element P is prime element. This is prime element. Actually in Z, prime and irreducible element both are coincide. But otherwise for every ring this is not coincide. But the ring, if the ring is UFD, then prime imply irreducible element. Prime element imply irreducible element. Also this is true if and this is if and only if condition. Also irreducible element imply prime element. Okay. Now let's see, if alpha equal to 1 plus I, is this irreducible element of Zi? Prove it. Consider 1 plus I, we can write this as A plus IB times C plus ID, and the conjugate of 1 plus I would be 1 minus I equal to A minus IB times C minus ID. Consider this is 1 and this is 2, and multiply 1 with 2, then these would be 1 square plus minus I square, this means 1 plus 1 equal to, this would be A square plus B square, and this is equal to C square plus D square. that imply 2 equal to a square plus b square times c square plus d square, that imply either a square plus b square equal to 1 or c square and c square plus d square equal to 2, or c square plus d square equal to 1 and a square plus b square equal to 2. And from this, that imply a plus iv is unit, and from this it imply c plus id is unit. Therefore, in Zi 1 plus I, if we can write this as a plus ib times c plus id, then either a plus ib is unit or c plus id is unit. If alpha equal to a plus ib and mod alpha equal to a square plus b square equal to p, where obviously this p is a prime number, then alpha is irreducible element of Zi. Similarly, if alpha equal to a plus iv with the condition mod alpha equal to a square plus b square equal to p square, if this is true, where p is a prime number and if p is congruent to 3 with modulo 4, then this alpha is irreducible element in Zi, and this is the shortcut truth. As for example, 2i is prime element in Zi because 1 plus 2i equal to 1 square plus 2 square, this is equal to 1 plus 4, this is equal to 5, and 5 is prime number. So 1 plus 2i is a prime element in Zi by these rules. If alpha equal to 3 plus square root of minus 5, this is irreducible element of z square root of minus 5. 3 plus square root of minus 5, we can write this as a plus b square root of minus 5 times c plus d square root of minus 5. We can write also its conjugate would be 3 minus square root of minus 5, then this would be a minus b square root of minus 5 c minus d square root of minus 5. If this is 1 and this is 2, multiply 1 with 2, then this would be 3 plus 5 means 3 plus 5 means 14 equal to a square plus b square, a square plus 5b square, sorry, c square plus 5d square, and 14 means 2 times 7. So from this line we can write either a square plus 5b square equal to 2 and c square plus 5d square equal to 7, a square plus 5b square equal to 7 and c square plus 5d square equal to 2, a square plus 5b square equal to 1 and c square plus 5d square equal to 14. C square plus 5d square equal to 1 and a square plus 5b square equal to 14. Notice here a square plus 5b square equal to 2. This is not possible. Similarly, c square plus 5d square equal to 7. This is also not possible. So this is not true. Also, this is a square plus 5b square equal to 7. This cannot possible. So these are not possible. That means only these are true. If a square plus 5b square equal to 1, that means a plus b square root of minus 5 is irreducible element, is unit element in z square root of minus 5. Also, if we consider this, then c plus d square root of minus 5 is unit element in z square root of minus 5. Okay, I hope my all viewers have understood clearly. So this element 3 plus square root of minus 5 is irreducible element in z square root of minus 5. I had seen few minutes ago prime element and irreducible element is coincide, but otherwise this is not coincide. Only when UFD, unique factorized domain, when the ring is unique factorized domain, then the prime element and irreducible element are coincide. Actually, in integral domain, every prime element is irreducible. Why? This proof is very easy proof. RB integral domain, and P belongs to R is a prime element of R, and P is obviously, since prime element P is non-zero non-unit element. Let AB belongs to R, that means P equal to AB. As P equal to AB, that means P divide AB, and as P is a prime element of the ring R, then P divide AB, that implies P divide A and P divide B. Suppose P divide A. If P divide A, that means there exists by definition a C belongs to R such that A equal to PC. And here I have got P equal to AB. Just put the value here. P equal to AB and A equal to PC. Then that implies P times 1 minus CB equal to 0. As P is non-zero and R is integral domain, so that implies 1 minus CB equal to 0, and 1 minus CB equal to 0, that implies CB equal to 1, which is equal to BC. That imply CB equal to 1 equal to BC, that imply B is a unit of R. By similar argument, if P divide A, that imply A is unit element, and since either B is unit or A is unit, if P equal to AB, then that imply P is irreducible element. That means when integral domain, then prime element always imply irreducible. But is the converse true? In integral domain, is irreducible element always imply prime element? No. Consider z square root of 5i and 6b element, then 3 divide 6, that imply 6 times 1, 1 times 6, 2 times 3, minus 2 times minus 3, 3 times 2, minus 3 times minus 2. We can write 3 equal to a plus square root of 5I b times c plus square root of 5I times d. If conjugate it, then 3 bar equal to a minus square root of 5IB times c minus square root of 5ID. Then consider this is 1, consider this is 2. Then multiply this, then this would be 9 equal to, here 3 bar equal to 3 obviously, 9 equal to a square plus 5b square times c square plus 5d square. Okay, and 9 we can write this as 3 times 3. Also we can write this as 9 times 1. Also we can write 1 times 9. When 3 times 3, this equal to a square plus 5b square times c square plus 5d square. But that imply a square plus 5b square equal to 3 and c square plus 5d square equal to 3. But there is no such AB such that a square plus 5b square equal to 3 and c square plus 5d square equal to 3 possible. So this is not possible. Other possibility is 9 times 1 equal to a square plus 5b square times c square plus 5d square. From here, c plus square root of 5I is unit, and this means a square plus 5b square and c square plus 5d square. From here, a plus square root of 5I is a unit. So, if we consider 3 equal to a plus square root of 5IB times c plus square root of 5ID, then either this is unit or this is unit. So 3 is irreducible element of z square root of minus 5. Okay, but 3 is not prime ideal. It is not prime element, but this is with the integral domain ID. So in integral domain, prime imply always irreducible element, but converse not true. Irreducible element not always be prime element in integral domain. But when the ring is PID, then prime imply irreducible. This is the if and only condition. Few minutes ago I have told you, when the ring is UFD, then prime and irreducible element are if and only condition. Actually, when PID, then that imply always the ring is UFD. So in PID, prime and irreducible both are coincide each other. Okay. Next I will see what is actually definition of unique factorized domain. I will see what is the associated. Let R is an integral domain and element A is associated to B if there exists an unit U belongs to R such that A equal to U times B. In ZI, 3 is associate in 3i because 3i equal to, we can write this as 3 times I. So 3i is associated with 3, where I is unit in Zi. That means associated mean a element A is associated to an element B if there exists an unit such that A equal to U times B. Then we can tell A is associated with B, where U is unit. Here 3i is associated with 3 because 3i equal to 3 times I, where I is unit in. I will see our actual goal of this lecture, unique factorization domain. What is unique factorization domain? Let R be the ring is integral domain. Then we say that R is UFD if every non-zero and non-unit element of R can be written as product of irreducible element of R. If we can write every non-zero non-unit element can written as product of irreducible element, and factorization of irreducible element is unique up to associate. As for example, in Z, consider the element 6. 6 we can write this as 2 times 3, or we can write this as minus 2 times minus 3. We cannot write 6 equal to 6 times 1 because 6 is not irreducible element. And notice 2 is associated with minus 2 because we can write minus 2 as 2 times 1. Similarly, plus 3 is associated with minus 3 because minus 3 we can write this as 3 times 1, where 1 is the unit element in Z. Actually, in Z we can write every element as product of irreducible element, and factorization of this irreducible element is unique up to association. So Z is always unique factorized domain. Similarly, if we consider 30 in Z, this 30 belongs to integer. 30 we can write this as 2 times 3 times 5. We can write this as minus 2 times minus 3 times 5. We can write this as 2 times 3 times minus 2 times 3 times minus 5. We can write this as 2 times minus 3 times minus 5. We can write 30 as product of irreducible element in product of is in many ways, but they are unique up to association. Notice 2 is associated with minus 2, 3 with associated with minus 3, also 5 with associated with minus 5. So we can write this as product of irreducible element. Also they are unique up to association. I hope my all viewers have understood. Also in field always imply UFD. Field always UFD because in field every element is unique. Every element has multiplicative inverse. We can write every element as product of irreducible element, and this product of irreducible element is unique up to association. Also in Euclidean domain always imply UFD, and PID always imply UFD. Since in PID every irreducible element is prime element, this is coincide. Irreducible prime, prime irreducible. So in UFD, since PID imply UFD, so in UFD every irreducible element is prime. This is our coincide. Today I will stop here. In my next video I will discuss elaborately unique factorized domain. Okay. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.